In recent laboratory experiments, physicists coaxed particles of light into navigating quantum circuits while moving forward and backward in time, simultaneously. Even with photons flipping their own arrow of time, one specific behavior remains more controversial, the phenomenon that broke Albert Einstein's sense of reality. Einstein's understanding of the universe relied on a strict rule called locality. This is the principle that an object is only influenced by its immediate surroundings. Under this classical framework, cause and effect are bound by a hard speed limit. Absolutely nothing can travel faster than the speed of light. Then came quantum entanglement. When two particles interact under certain conditions, they become part of a single, unified quantum system. You can separate those particles by inches or by thousands of miles, yet they remain mathematically locked together. If you affect one, the other changes instantly. Einstein vehemently rejected this concept, famously dismissing it as spooky action at a distance. He maintained that the theory was an incomplete description of nature, insisting that some hidden, underlying mechanic must be at work. This conflict set the stage for one of the greatest debates in modern science. It forced physicists to ask, are these particles following pre-programmed hidden instructions like Einstein believed, or does the physical reality of a particle literally not exist at all until the very moment we look at it? To understand exactly what bothered Einstein, we first have to look at superposition. In our everyday world, an object has a definite state. A coin on a table is either showing heads or tails. But in the subatomic realm, before a particle is measured, it exists merely as a wave of probabilities. It is essentially spinning both up and down at the exact same time. When two of these unmeasured particles interact, they can become entangled. They merge into a single quantum system. Even if you take these two probability waves and drift them to opposite ends of the galaxy, that invisible mathematical link persists. The critical moment happens during observation. The second you measure the first particle, its superposition collapses. It drops the probabilities and adopts a definite single state. Let's say it locks into spinning up. At that exact fraction of a second, the second particle reacts. It instantaneously collapses out of its wave state and adopts the corresponding opposite configuration, spinning down. There is zero time delay. A physical signal does not travel through space to tell the second particle how to behave. This instantaneous coordination ignores distance entirely. It shatters classical assumptions about how cause and effect operate in our known universe, leaving physicists scrambling to explain a mechanism that, on paper, looks like magic. In the year 1935, Einstein and his colleagues Boris Podolsky and Nathan Rosen published a paper attempting to rationalize this. Known as the EPR paradox, their work argued entangled particles possess hidden variables, essentially pre-programmed instructions agreed upon the moment they were created. To explain it, Einstein used a simple analogy. Imagine putting a left glove in one box and a right glove in another. If you separate the boxes across the globe and open one to find a left glove, you instantly know the other box holds a right glove. Under this logic, no spooky communication is actually happening. The gloves were always left and right. The particle states were determined from the start, preserving a predictable classical reality. In 1964, John Stewart Bell designed a way to settle the argument. He realized that if Einstein was right and the particles were pre-programmed like the gloves, there would be a very strict mathematical limit to exactly how often their measurements would correlate over many trials. When physicists ran the tests, the results broke Einstein's statistical limit. The particles showed coordination mathematically impossible for two independent preset objects. The math proved that the particles are truly undefined probability waves until the very moment of measurement. Einstein's hidden variables simply weren't there. The act of measuring one physical entity dictates the reality of the other across space. This spooky action is entirely real, proving that our universe is governed by instantaneous, long-distance relationships at its most granular level. If two particles can dictate each other's state instantly across vast distances, it raises an obvious question. Can we use this link to send information faster than the speed of light? The short answer is no. Because the final state a particle collapses into is completely random, you cannot control whether it locks into a spin up or spin down position. Without the ability to manipulate that outcome, you can't use the connection to encode or transmit a coordinated message. You can observe the correlation instantly, but you cannot exploit it to bypass the cosmic speed limit. Thanks to this inherent randomness, Einstein's theory of general relativity survives intact. This theoretical debate has transitioned into a race for practical application. Entanglement now serves as the primary foundation for quantum computing, where particles existing in multiple states simultaneously allow for processing power that dwarfs traditional silicon chips. It is also the basis for quantum cryptography. Because the mere act of observing a quantum state forces it to change, any attempt by a third party to intercept an entangled signal immediately alters the data, alerting the sender, and allows for the creation of completely unhackable communication networks. Einstein viewed entanglement as an absurd flaw in quantum mechanics, a glitch in the math that had to be corrected. Yet that very glitch has proven to be the key to our technological future.